Okay, this is the sort of lesson in our mathematical journey where it's kind of like a make or break. If two things are either going to happen. One's going to be you'll look at all this and you'll be like, what on earth is going on? There's so many things we've learned, I can't keep up. Or it's going to be a good summary of everything we've done in polynomials and everything's just going to click and you're just going to be like, that's why we do everything. There's all these random processes, but they all kind of lead up to this, which is kind of cool. So I really hope that this is a really nice end to the journey, even though there's still more to come. Okay, so last lesson, I've got it up in the top corner here. We looked at the remainder theorem. So that just said that if I'm dividing by something, so in this case here, if I'm dividing by x minus 3, then that positive 3, so like the opposite sign, that positive 3, when I substitute that into the original, is the remainder, 28. So that's what we found out last lesson. So it gave us a way of checking whether this thing has a remainder. And we kind of want to get to the point where we don't have remainders. Like the whole point of doing this this long division is so that we have a nicer thing that we can graph. So you'll notice that here we've started with this thing. It's like it looks nice, but we can't graph it. It's a cubic. What we end up with, so this thing down here, which is not letting me highlight, so this thing down here, that is something we can graph, and I did graph it. I did graph something like similar like that. I can graph this quadratic. I can graph this little thing there, and then I just raise the whole thing up 28, and that's something I can graph. Whereas the x cubed is something I cannot. So this whole topic and the whole last topic is, or the reason we do all this is so that we can draw a picture. That's the end game, is to draw a picture. And we did all that stuff with quadratics so that we could draw a picture. So I want to make a little bit of a comparison. So we had our quadratics, which was all of the year 10 stuff last term, which just means I've got x squared, blah, 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 blah. And then this topic, we've started to look at cubics a little bit more. So cubics in the, most of the things that I was long dividing started with a cubic, like this x cubed, and well, that's the only example I did, but the long division one, x cubed, there was a reason for that. And so the cubic, x cubed. Now, there's two things, I guess, that stem from each of these that allow us to draw it. And it's that the nicest versions of a quadratic you'll be able to factorize. So you'll be able to factorize. And what you'll end up with is two sets of brackets, x minus a, x minus b, or something like that. Once I have that, these two things here, they're my, you might want to call them your x-intercepts, or there's a couple of different words for them. Actually, let's write them. So these have a bunch of different words. They're either your x-intercepts, or, let me move this, or another word is roots, or another word is actually zeros. So the reason they're called zeros is because normally you solve this equation, and that's how you find your x-intercepts. You just like having that equal 0 and having that equal 0. They're just your zeros. And you'll notice that every time you factorize a quadratic, which is to the power of 2, you end up with two sets of brackets at most. Sometimes you end up with the same thing squared, so you might end up with this squared, and that's the same, but that would just mean that that's an a. So essentially we're doing the same thing. Now, when another thing, the reason we use the word factorize, that might not have been very evident, because you know how we have expand and factorize, and when you expand, you're breaking everything apart. Expand actually kind of makes sense, whereas factorize is just like a really weird word. What you're actually doing is you're getting some quadratic term like this, I don't know, and you're turning it into a product of its factors. Now, its factors are a little bit strange because when you think of like the number 10, you break that into 2 and 5. That's its two factors. But they're just two things that multiply to give 10. So these things are the factors. So in this case, I have some quadratic equation. Its factors are just these linear expressions. So linear expressions are their factors. And sometimes it'll say that, sometimes you'll be asked to find the linear factors of a quadratic. That just means factorize it into two things you can multiply together to give the original thing. That's what that means. And so you'll notice that when we factorize stuff, we don't have a remainder, so we don't have something added on to the other end. And that was because most of the time when we were factorizing things, it would work. Like we would be asked to factorize it, knowing that it was possible to factorize it. But then when there were things where we couldn't factorize it, we needed to come up with a new thing that we could do that would enable us to have some sort of a remainder. And that thing was completing the square. The square. So that gave us something like x minus a squared plus something. And so then what we were able to do then is rewrite our thing that we couldn't graph into something we can graph and then raise it. And so we've actually done this whole process before. So there's two nice ways of doing this. There's factorizing, or there's half factorizing and having a remainder. And so then we've ventured onto cubics where we've kind of got the same problem, except we're not able to easily factorize a cubic. We can't just look at this thing and be like, oh, look, I can think of two numbers that add to 5 and times to 6, and then what on earth do I do with this 4? Like, we can't, there's no real nice way of doing this. So what we have to do is we have to think of a factor. So most of the questions, well, all the questions we've had so far, they give us a factor. So like this question I went over, it said show that this is a factor, and then I was able to rewrite it using this, and you can see that when I ended up with this 0 here, I didn't have a remainder on the end. I just was able to represent this thing in terms of its factors. So we've kind of got two things we can go from here. We've got the, let me write it here, the remainder theorem. So that ended up, because when we were doing this thing over here, we ended up with two sets of brackets and then a plus something. So quadratic linear term plus something. And now what we're going to have is our factor theorem, which is today's lesson, which has a quadratic and a linear term with no remainder. And to get to each of these, we have to use long division. Okay, so that's kind of our journey. All the factor theorem says is that if your linear term is a factor, then when I substitute a, it doesn't give me the remainder like it did back here. It doesn't give me the remainder, it gives me 0, because 0 is the remainder, because there is no remainder, because I can factorize these into nice things. That's all this is saying. So in other words, you do the exact same thing as with the remainder theorem. You just substitute this a into your original polynomial, substitute this a into your original polynomial, and if you don't have, if you pop out a 0, the 0 pops out, then that means it is a factor, which is what you want. Now, okay, so let's go over the first one. It tells us what one of the factors is. It's saying, prove to me that this thing is a factor. So it's essentially the same thing. It's saying, okay, well, here's my long division. Now, we've already done this, essentially. Show that this is a factor. That just means that when I perform my long division, I'm going to end up with 0. So I don't know if you want me to go over this because it's going to take a little while, because it's polynomial long division. Maybe I want to do it fast. Maybe I'll do a fast version of it. We'll do that. So maybe skip like 2 minutes if you don't want to watch me do a long division, but I'm going to do it. 2x cubed, that's going to be in the way. 2x cubed minus 7x squared. Also, I'm super out of time, so if I make a mistake, I'm actually recording this like the second I'm going to upload it. So if I make a mistake, I am definitely not restarting. Okay, how do you do this junk again? Just kidding. You go, all right. I care about this, and I care about this. How many x's go into 2x cubed? There's a 2, don't want that in red. There's a 2x squared left. 2x squared times x is 2x cubed. 2x squared times minus 2 is minus 4x squared. I take the negative, draw my subtraction line. That's nothing. Minus 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 is a minus plus. Minus 7 plus 4. Am I going to appear really stupid here? Minus 7 plus 4. Minus 3. Minus 3x squared. I have to check that. Yeah, okay. Bring that down. Okay. How many x's go into minus 3x squared? I'm pretty sure minus 3x go in. Oh, look at this. I'm ending up with the same thing. That's nice. Okay. Minus 3x times x is minus 3x squared, which is what I want. Minus 3x minus 2 is plus 6x. Minus, boom, boom, that's nothing. Minus 3, minus 6, minus 9x. Bring that down, plus 18. How many x's going to minus 9x? Minus 9. I better end up with a remainder here. Oh yeah, minus 9 times minus 2 is 18. Whoops. That square tells me I'm done. Okay, so I'm finished. Hence, show it as a product of its factors. So I guess the way I just think about this is why I've kind of put this in the top corner too. Have a look at my original thing. 9,947 is the same as 65 times 153, and then I add on my remainder. But this time I don't have a remainder, so it's going to be this times this equals this, and that should make sense because that's just like the opposite of dividing is timesing. Okay, so 2x cubed minus 7x squared minus 3x plus 18 equals, oh, I forgot to write what I did up here. What was the number up here? Did I even say it? Oh, it's because I pressed back when I was using the thing. So making excuses. 2x squared minus 3x minus 9. Okay. Okay, so my problem here is that, let's suppose this was just an isolated question and it said graph this. I couldn't do that unless someone told me what one of the factors are, x minus 2. So now that someone told me that, I'm able to forget about this thing. I can graph this. Now, if this was a more clever question, this would say a product of its linear factors. And you'd notice that this thing is not linear, it's quadratic. So what I can do is I can factorize this thing. So I can do like the a plus b, a times c plus b thing. And what I'm going to skip that. What you'd end up with is this. I don't want to spend too long doing that. But you can see that all these different things that we've done before are kind of combining into this one thing. So now what I can do is, and I haven't really shown you how to graph this, but that's something that's coming. I can find the zeros of this, so all the x-intercepts. So here is 2, here is 3, and here is minus 3 on 2. So these are the parts where it cuts the axis, and then I'm going to show you how to draw what the curve looks like soon. But now that I have it represented in a beautiful factor like this, I can draw it. And that's the end game. We're going to get towards drawing it. I haven't shown you how to do that properly yet. It's just about getting it into some form where I can draw it. And so you'll notice I did start with a cubic, and now I have three sets of linear factors, or 3 sets of brackets. So that's the end game. I can't draw that, but I can draw this. Now, what I was saying before was I don't know how to represent it like this without being given this. This just talks about the zeros, which is what I spoke about before. So let's do a question where it doesn't give us that. So this one just says factorize it, and then tell me what the zeros are, which is exactly what this question was doing. It said express it as a product of its factors, factorize, and then we're not going an extra step, but that's essentially the same question. So I want to factorize it and then find its zeros. So I found its zeros just funsies, but that's what we're going to be asked to do now. And this is as far as we're going. So the end game is to be able to look at something like this and then factorize it. So you would have been able to do this. This is something you can do. You can tell me where the zeros are of something like this. You can factorize it. You can use a quadratic formula. You can complete the square. There's all these different things you can do. But the second there's a cubic on there, we can't do it. So you're going to hate this slightly, but normally you'd be like, okay, well, I need to divide it by something. I want to divide it by something such that I don't end up with a remainder. That's what factorizing is. I'm expressing something in terms of its factors without a remainder. So I need to figure out x. Oops. I need to figure out x minus something such that I don't end up with a remainder. Now, I want you to think about what happens when you do end up with a remainder. When you end up with a remainder, you get this value here, you substitute it into here, and what happens? When you have a remainder, there'll be a remainder. But if there's no remainder, you'll end up with 0. So what you need to do is think of a clever number that you can find for question mark, such that when you put it in here, you end up with nothing. That's the goal. And you've done this before, like when you have x minus 3, x minus 2, you know that the zeros are 3 and 2. So if you put a 3 in here, that's 0. Or if you put a 2 in there, that's 0. So you're just trying to find one of those sets of brackets numbers. You're just trying to find one. Once you have one, then you can divide it, and then we can do this whole process. But I just need to find this question mark. So in finding this question mark, there's a trick. it is a bit of guess and check. There's no real beautiful way of doing it. It's not like completing the square where there's a set of rules that you follow. This is a little bit different. So you do need to kind of guess, but at the same time, there are clever guesses you can make. And what you're trying to make is you're trying to find factors of 30. So what you'll notice that of the constant. So what you'll notice that every time you don't have a remainder, it's normally the fact that your value here is a factor of this. So I just want to prove that to you. Have a look in the remainder theorem one. See, I've got the constant 4, and I've got 3 here. Is 3 a factor of 4? No. That's why there's a remainder. If you look at the long division here, same thing. 4, is 3 a factor of that? No, that's why there's a remainder. Here, 4, why did I use 4 and 3 for every example? Let's look at this one. The 5, is that a factor of the constant, 30? Yes, it is. And have a look, the remainder is 0. Now, it doesn't work always. That doesn't mean that I can put all the factors of 30 in here and it's always going to divide. That wouldn't make any sense. That would mean there'd be like a million sets of brackets. There's only 3 sets of brackets. So you have a 3 in however many factors there are of 30 chance of finding your factor. And depending on who you are, you might find a different factor to somebody else. Okay, so I guess the first thing you want to do is list your factors. It's a little bit annoying because it's a minus 30, so that means you have to also list your negative factors. So minus 1, 1, minus 2, 2, minus 3, 3, like there's heaps. So what you kind of do at this point, you just kind of guess and check. So I go to P of minus 1. That's equal to a minus 1 shoved into here. I have the answers up here. I'm not going to waste your time with checking it. But if I put a minus 1 in there, I get minus 6. So therefore, not a factor. I put P of 1 in there, I get negative 60. Therefore, not a factor. If I put P of 2 in there, I actually do get something. No, what did I do 2? If I put negative 2 in there, I get 0. So that means negative 2 is a factor, and therefore therefore x minus minus 2, or x plus 2, is a factor. And so that's the thing I should now divide by. So 2x cubed minus 3x squared minus 29x minus 30 is equal to, and now I'm going to be able to figure out that it's x plus 2 and then a set of brackets with an x, this will have a quadratic in it. So now what I'm going to do is my long division. So I'm going to go all that again. So to be honest, if this was me in my working out, like in a question, and yes, this does get asked, like to do this whole process, I'd probably do this as a little aside and like draw a bubble around it or something. Anyway, let's go. So how many x is going to 2x squared, 2x cubed, sorry, 2x squared. So then that, let me circle it, that times that is 2x cubed. That times that is 4x squared. Take it away. That's 0. And then that's minus 7x squared. Bring down the 29x. So then x, how many x's go into this? Minus 7 x's. So then minus 7, something please. Minus 7x times x is minus 7x squared. And then minus 7x times 2 is minus 14x. Take that away. That's 0 minus plus, I'm going to screw this up, minus 29 plus 14 is minus 15. I just need to make sure because I'm stupid. Okay, and then how many x's go into minus 15x is minus 15. Good. Minus 15 times 2 is minus 30. So that's what I want. When I minus that, I get 0. So I'm done. So that means this in here is going to be 2x squared minus 7x minus 15. Now the question wants us to solve the equation. So let's bring that down here. So basically, instead of having to solve this thing, which is impossible unless you wanted to use the cubic formula, but the cubic formula is beyond disgusting. That's the same as just saying, okay, well, if I had x plus 2x, look up the cubic formula if you want, but I assure you this is probably faster. Actually, it's probably not, to be honest, but I don't want to have to memorize the cubic formula. It's not many reference sheets. So now, after all this working out, who cares about any of it? I only care about solving this equation. So now you kind of got a choice here. You know that one of the zeros is 2, or sorry, minus 2. Now you have a choice as to how you solve this one. You can solve using quadratic formula, you can complete the square, you can factorize, whatever you like, I don't really care. But what I'm going to do is make another little aside. You can see how much working out is involved. Let's do the a times c plus b. So this one probably. A times c is minus 30, plus b is minus 7. Two numbers at times to 30. I'm thinking of 3 and 10. Let's go with 3 and 10. One of them needs to be negative. So the minus 10 plus 3, that makes sense. So I'm going to break this up. I'm going to use big brackets into plus 3, x minus 10, x minus 15. I'll put the 10 and the 15 next to each other because there's a 5 there. X plus 2. So I'll factorize. I can only bring an x out of that. So it's 2x plus 3 minus. What on earth do I bring out of this? 5 minus 5. 2x plus 3. Okay, good. So now I've got x plus 2, 2x plus 3, x minus 5 equals 0. So that means x equals, actually let's do it properly. So I've got either x plus 2 equals 0, I've got 2x plus 3 equals 0, and I've got x minus 5 equals 0. X equals minus 2, x equals minus 3 on 2, and x equals 5, and they're my zeros. Oh, look at that. You want a full page of working out for a question? You got it. But how cool is that? It's so many things in one. Like, we brought long division into factorizing, into graphing, into... it's just so much. But I think it's really beautiful. Anyway, I went holy moly 22 minutes. Let's just goodbye.